all. Today we're going to be working on topic 5, reactions in solution. So our learning goals for today are to explain collision theory and its relation to reactions in solution. We're going to represent reactions in solution using total and net ionic equations. We're going to define and identify spectator ions in a reaction. So according to collision theory, all chemical reactions must involve collision between reacting entities, right? And that makes sense. If the reactants can't come together, no reaction's actually going to take place. So if there are more collisions, there's going to be more reactions. So if we consider reactions that happen in the solid state, they're typically going to be slower because our surface area is less, allowing for less collisions. So if we look at this picture here, we have a solid material here reacting with these blue spheres. The only place where a reaction can actually take place is on the surface where these entities can actually come together. Now, if we have a reaction in solution, we're going to find that those are typically going to be faster, okay? Because this allows us to have the greatest surface area, right? These molecules are broken down into their simplest components, especially if they are soluble, right? Because if they're soluble, that means that it's interacting with water and has been split apart, right? If we have an ionic compound, it's going to dissociate into its respective ions. If we have a covalent compound, it's going to break down to the individual molecules, right? And that gives the greatest surface area to allow for reactions to take place and will increase the reaction rate. So what we're going to try to do today is to analyze what actually happens for reactions in solution, right? Because we've learned how to go through and write out balanced equations, right? But we're going to actually think about what is happening in solution to each of these entities, okay? And we know that if we have soluble ionic compounds, they actually will dissociate in solution. And we're going to actually show that using a few different types of equations. Okay, and the first one that we're going to look at is a total ionic equation, which shows all highly soluble ionic compounds in their dissociated form. Okay, and this will give us a better representation of what's actually happening to these reactants and products in solution. So let's consider this example. Here we have silver 1 nitrate reacting with sodium chromate to make silver 1 chromate and sodium nitrate. Okay. The reactants are both aqueous, and silver chromate is a solid, and sodium nitrate is aqueous. Okay, if we weren't sure about the states, we can always go back on our solubility table to check, and we'll talk a little bit more about that as we work our way through. So if we look at this reaction, while it does show overall what's happening in the reaction, it is not actually fully accurate, okay, for what's actually happening in this solution. Because all soluble ionic substances will dissociate into their respective ions. So what we're going to see and learn is how to write out a total ionic equation. And that'll show all of the soluble ionic compounds in their dissociated form. Okay, so all that practice that we had with writing out dissociation equations is going to come back because we're going to be doing that to this overall balanced equation. Okay. So let's take this example a little bit further. So we have this reaction here. Okay, so we have silver nitrate reacting with sodium chromate to make silver chromate and sodium nitrate. Okay, so what we're going to try to do is write out a total ionic equation. And all we're going to do is anything that we see as aqueous, we're going to split apart and write out a dissociation equation for that. So underneath here, if we look at AgNO3, okay, that's going to break apart into 2Ag plus in the aqueous state plus 2NO3 minus Aq. Okay, all we're doing is writing this in the dissociated form. We're putting 2 as our coefficients here because based on our balanced equation, we have a coefficient of 2 in front. Okay, we're going to do the same thing for sodium chromate. So if we look at this, we have Na2CrO4. Okay, so this is going to split apart into 2Na plus Aq, okay, and there's 2 Nas because of the subscript here, and CrO4, which carries a charge of 2 minus. Both of these are going to be aqueous. Okay. Now, if we look at silver 1 chromate, it's in the solid form. Okay, so that tells us that it actually does not dissociate in solution and remains as a solid. So we will write that as is. Now, if we look at sodium nitrate, it says AQ. So we're going to split that into the dissociated form. So we have 2Na plus AQ plus 2NO3 minus AQ. Okay. I wrote this out like this just because I couldn't fill it all into a screen. And then what we're going to do is just consolidate everything. So here we have 2Ag plus AQ plus 2NO3 minus AQ plus 2Na plus AQ plus CrO4 2 minus AQ yields silver 1 chromate plus 2Na plus AQ plus 2NO3 minus AQ. Okay, and this right here is a total ionic equation. Okay, so it takes our overall balanced equation and separates anything that's in the aqueous form and separates it into its respective dissociated ions. If it's in the solid state, it remains as is. Okay, so if we actually think about it and we're carrying out this reaction, this is what's happening. When we're writing AQ, these are actually in the dissociated forms as written in this total ionic equation. Okay, so now, are all of these ions actually involved in the reaction? Okay, and what we're going to find is no, some of them actually aren't, and they get a special name. Okay, and they're called spectator ions. Okay, a spectator is an entity such as an ion molecule or ionic solid that does not change or take part in a chemical reaction. Okay, so if we look at this, right, we're looking to identify spectators, we're looking for entities that are on the reactant side and the product side that are identical. Do you notice any? If you thought NO3, you're right. So if we look here, its structure has not changed. It's the same. Okay, so this is a spectator. It is there. It is watching the reaction, but really it's not actually taking part. Okay, do we notice any others? If you said Na, you're right, because here we see 2Na plus, and here we see 2Na plus. Okay, so that's on both sides of these. But if we look at the rest of the substances, right, 2Ag plus, we can't find that over here. CrO4 2 minus, we can't find that over here. So these two are the only spectator ions that we have. Now, why do they get the term spectators? Okay, if we think about if you're going and watching a basketball game, right, while the Raptors were winning their championships, right, all the fans in the stadium are called spectators, right, because they're there, they're taking part in the festivities, but they're not actually involved in the game. Right, and that's the same scenario here for the sodium ion and nitrate ions. They are there during the reaction, they have a front row seat, but they are not actually taking part in the reaction. Okay, so to indicate the ions and molecules and ionic solvents that are actually involved in the reaction, we're going to actually remove the spectator ions, and that will give us a net ionic equation, okay, which is a way of representing a reaction by writing only those entities that are specifically reacting. Okay, so if we have this reaction, we're just going to cancel out our spectator ions. And this is no different from collecting like terms during math. Okay, and we have the same thing on each side of an equal sign, and it would cancel out, where our arrow here is treated as an equal sign. Okay, so we're going to just basically rewrite our equation, omitting our spectator ions. And now we get 2Ag plus AQ plus CrO4 2 minus AQ yields Ag2CrO4 in the solid form. Okay, and during the reaction, this is actually what's happening. The silver ion is combining with the chromate ion to generate silver 1 chromate. Okay. So our rules for writing a net ionic equation is we need to start off with our balanced chemical equation. Okay. From there, we need to identify whether the reactants and products are soluble or insoluble, and we're going to use our solubility table to do that. From there, we're going to rewrite the formulas of all highly soluble ionic compounds as dissociated ions. Okay, anything that's AQ, and that will give us a total ionic equation. From there, we're going to cancel any of the identical entities out, so we're going to get rid of our spectator ions, and then just rewrite it with what's left over. Okay, and that will give us a net ionic equation. Okay, so let's try a few examples. So in here it says, write the net ionic equation for the reaction of zinc metal and aqueous copper 2 sulfate, and then write a statement communicating the meaning. So in here we have to write our balanced equation. So here we have zinc in the solid form. It's a solid because it's a metal, reacting with copper sulfate. It tells us in the question that it's AQ. Okay, that this, because it's a single displacement, zinc is going to try to displace copper. So copper is going to be displaced, and that's going to be in the solid form. And we're going to get zinc sulfate AQ. Okay, so to go through, write a total ionic equation, we're writing anything in the AQ form in the dissociated state. So if we look here, zinc is solid, so that stays as is. We have copper sulfate AQ, so we're splitting that apart. It's Cu2 plus AQ and SO4 2 minus AQ, right? And we just got to double check the charge on sulfate, and if we look on our polyatomic ion sheet, we'll see that it is 2 minus, so that means copper's charge must be 2 plus. Here we have copper solid, so we're keeping that as is. And then we have zinc sulfate AQ, so we're going to have to separate that into zinc 2 plus AQ and SO4 2 minus AQ. Okay. From there, we're canceling out our spectator ions, so we see SO4 on both sides. And then from there, we can rewrite. And in this reaction, we have neutral zinc in the solid form reacting with the copper 2 plus ion aqueous, and that generates copper solid and the zinc ion. Okay. If we look at this a little bit further, okay, we can actually say that there's an electron transfer that's happening. Okay, so zinc is donating 2 electrons to copper, okay, to make it neutral, and zinc is losing those 2 electrons, so it's becoming 2 positive. Okay, so this is another way of being able to analyze it a little bit further. Do I expect you to be able to do that? Not necessarily, but as an extension, I think it's a great thought process. Okay, so placing solid zinc in any aqueous solution containing copper ions will produce solid copper and aqueous zinc ions. Okay, if we look at sample problem 2, it says write the net ionic equation for the following double displacement reaction. So we have potassium iodide AQ plus PbNO3 So we have our double displacement, so they're going to switch partners. So we're going to generate KNO3AQ and PbI2 solid. We would have to look on the solubility table for these states. If you guys do remember during the chemical reactions unit, this is a reaction that we did in class where we mixed the two clear solutions, okay, of potassium iodide and lead 2 nitrate, and that generated that yellow precipitate, if you remember. Okay, so to write out a total ionic equation, anything AQ we're writing as in the dissociated form. So Ki is AQ, so that's 2K plus AQ plus 2I minus AQ. Remember, it stays I minus, we're not writing I2. Okay, this is still just dissociation when we're writing these out. PbNO3 2AQ, we're splitting those up, so it's Pb2 plus AQ and 2NO3 minus AQ. Here we have 2KNO3AQ, so we're splitting that up. So 2K plus and 2NO3 minus. PbI2 is a solid, so it stays as is. We're going to get rid of our spectator ions, so that's K plus and NO3 minus, and then we're going to rewrite whatever is left over. Okay, so we have 2I minus plus Pb2 plus generates PbI2. The order you write it doesn't matter. If you want to make it a little bit neater, you'd write maybe Pb2 plus and then 2I minus to match over here, but it really doesn't matter the order at which these are presented. Okay. Last one. So here we're asked to write the net ionic equation for the following double displacement. So we have HClAQ and NH4BrAQ. Okay, I'm not going to go into too much detail on this one, but I do want to make a comment. So if we go through, write out our balanced equation, we get HBrAQ and NH4ClAQ. We notice everything's AQ, so we're going to write everything in the dissociated form. And then what we notice is that everything actually cancels out. So because everything cancels out, there was no reaction that actually took place. Okay, and if we remember back to our chemical reactions unit, we said a double displacement reaction will only happen if a precipitate forms, a gas is generated, or it's a neutralization. Okay, and this is one of the reasons, right? Because in this case, there is none of those scenarios generated, right? The products are both AQ. So all we really did was dissolve these compounds in water. No new compound was actually formed. Okay? So that ends today's lesson, where we look through to write out total ionic equations, identify spectator ions, and write out net ionic equations.